Hello. This is a talk that I've given a few times before, mostly to college students, but it's appropriate for talented middle school and high school students as well. It's completely elementary, which elementary in the sense of does not require any prerequisite knowledge of any advanced mathematics, anything like calculus or anything like that. All it requires you to know is what the integers are, what the prime numbers are, and what a little bit about what functions are, which we'll talk about as we go through the talk. The title of the talk is Prisoners, Involutions, and Fermat's Two Squares Theorem. So the theorem of Fermat, the two squares theorem of Fermat, is a very important and fundamental result, and it's also just about 400 years old. The proof that I am going to outline for you at the end of this talk of this theorem was actually discovered in my lifetime by a mathematician named Zagier. And the interesting thing about it, or the sort of surprising thing about it, is that the proof is completely elementary. It could have been found by a sufficiently clever person in the 1600s when the result was first stated. And it's sort of surprising that something so elementary and so short, the argument is very short, was not discovered for hundreds and hundreds of years, and is again accessible enough for middle school and high school students to understand. So that's the goal of the talk. We'll start the talk with a brain teaser, which I think I have given as extra credit on one of the homework sheets. A brain teaser that is fairly well known. You may have heard it before. And we'll introduce an idea to solve the brain teaser, and then we'll show how using that idea, which is a very simple idea at heart, actually allows us to solve this more sort of advanced problem about the prime numbers. So the setup for the brain teaser is there is a prison, and there are 1,000 prisoners in the prison. I've drawn 10 of them there in their cells. Those boxes there are numbered cells 1 through 10. So you can imagine 1,000 of them stretching off this way. And the X's denote the fact that the cells are locked with prisoners in each one. So the prison is overcrowded, and they decide to let some prisoners go free, sort of semi-randomly. And the procedure that they hit on to decide who goes free is that what they're going to do is they're going to go sort of sequentially through the cells and lock and unlock them using the following procedure. So step one is they'll go through each cell, and they will change every cell. So you can see, for instance, that if we say O to be open, they'll go through every cell in step one, and they will open them all. In step two, they will go through every second cell and change the status of the lock on that cell. So if it's unlocked, they'll lock it, and if it's locked, they'll unlock it. So in this case, what will happen is, since all the cells are unlocked, and again, this is stretching off to 1,000 cells. So every second cell, they'll change the lock. So they'll pass over the first cell, they'll relock the second cell, they'll relock the fourth cell, they'll relock the sixth cell, and the eighth cell, and the 10th cell, and so on. Step three, they're going to go every third cell, and they're going to, again, change the lock on every third cell. So in this case, they're going to relock cell 3, but now they're going to actually re-unlock cell 6. They're going to lock cell 9. They're going to re-unlock cell 12, if you can imagine that, and so on and so on. Then step 4, they're going to do the same with every fourth cell, and the process continues until they've done steps 1 through 1,000. And then at the end of all of those steps, they will let anybody whose cell is unlocked go free. And the question is, which prisoners go free? How many prisoners go free, and which cells are they in? So we've done the first 4 steps, the first 3 steps actually. So you can see the first 4 steps. Step 4 is they'll unlock cell 4, they'll unlock cell 8, they'll unlock cell 12, or actually they'll I guess they'll be relocking cell 12, and so on. Step 5, you can see they're just going to lock cell 5. They're going to unlock cell 10. Step 6, they're going to lock cell 6. They're going to do more, but I'm only sort of drawing what they're going to do to the first 10 cells. Cell 7, they're going to lock. Cell 8, they're going to lock. I mean, you can kind of see cell 9 actually unlock, cell 10 they lock. You can actually see, and then after that, steps 11 through 1,000 don't affect these first 10 cells. So actually, you can see which cells are unlocked at the end, which of the first 10 cells end up locked and unlocked. And if you see, it's the ones that have a circle on the top there. And if you look closely enough, you'll see that the cells that are unlocked are cells 1, 4, and 9. Cell 1 gets unlocked at the beginning and stays unlocked because none of the other steps affect it. Cell 4 gets unlocked in the first step, and then it gets relocked in the second step, and then it gets unlocked in the fourth step, and then that's it for that cell. And cell 9, the same thing happens. It gets unlocked in step 1, relocked in step 3, and unlocked in step 9. So already, I think, if you're thinking a little bit, you can sort of see that which cells get unlocked are sort of a function of maybe some sort of divisibility of the number of the cell. Numbers like 5 and 7, which are prime numbers, only get changed twice. They only get changed on step 1 and on step 5 or 7. So you can sort of see already that prime numbers, prisoners in prime numbers are out of luck because their cell's going to get unlocked and then locked, and that's it. And so their cell is going to end up locked. It's still an open question, although you might have guessed the answer already as to which prisoners are going free at the end of this entire process. So we'll come back to this brain teaser. You could think about it as we go through this idea that we're going to use to solve it. But that's the brain teaser. So you may have heard the brain teaser, by the way, with lockers instead of prisoners, but I like to make the stakes as high as I can. So we'll bring it to it. We'll make them prisoners instead of lockers. All right. So what we're going to do now is we're going to talk about an idea that we're going to use in this to solve this brain teaser, and the idea is about involutions. So let me tell you what an involution is. So at the high level, I'll just write down the definition, and then I'll sort of talk about what it means, and we'll sort of break it down. So an involution is a function. So an involution is a function on a set S. So and it takes S to itself. So a function is just a rule that says for anything, for any little s in my set S, if I start with S here, little s here, then a function is a rule that tells me where it goes. And everything here goes to exactly one thing over here. But again, things over here might go to, they might collapse. Multiple things here might go to the same thing here. There might be things here that don't get hit by the function, and so on and so on. So this is just a function. What makes a function an involution is the rule that, so an involution is a function f, from a set to itself, satisfying f of s equals s for all s in S. So what that means is if you do the function twice, you get back to where you started from. You get the identity. So this is a little bit abstract. So let's give some examples. And I think when you look at examples, you kind of see what's actually going on. So so here are some examples. So let's consider the function f from the integers to the integers. This, for various reasons, the set of integers is denoted by this sort of weird-looking z. Stands for Zahlen, which is the German word for number. And let's define f of x to be negative x. And this is a rule that tells you if I have an integer here, what happens to it? It goes to the negative. So you can see that if you do that twice, if you take f of x, you get negative x, and then if you take f of x, f of x is the same as f of negative x, which is negative negative x, which is x. Well, that's blurry over there. Apologize. So that shows you that that's an involution. So here's another involution. You can check that. Let's call it g. You can make another function, and you can define it by g of x equals 1 minus x. That one is also an involution, and I invite you to convince yourself of that. The same idea. Let me give you another one, and this one I think is the one that I'm sort of going to be the most interested in. I'm just using different letters to distinguish between these functions. Let's take the set to be a finite set. Let's take it to be the numbers 1, 2, 3, 4, 5, 6, 7 to itself. So this is just a set of 7 numbers, and we'll define h of. So if I want to give you a function on a finite set like this, I just have to tell you where everything goes. So let's say I want h of 1 to be 2. Well, now if h of 1 is 2, h of 1 has to be 1, so h of 2 has to be 1. So that kind of, already you can see there's kind of it's a pretty important restriction on what this function can do. I can't just choose anywhere for everything to go. Let's me say h of 3 is 6, and then let me say h of 4, let's just say it's 4. Now if you think about it, h of 6 is going to have to be 3 for the same reason as these two. And then let's make h of 7, let's say it's 7, and then h of 5, let's say it's 5. So this is a function on, that takes the set 1, 2, 3, 4, 5, 6, 7 to itself. And it's actually a permutation, as you can see, that everything in the target set gets hit by exactly one thing in the domain. But this is an involution, and the way to check that is just if you start at 1 and you do the function twice, you get back to 1. If you start at 2 and you do the function twice, you get back to 2. If you start at 3 and do the function twice, you can do it once, you get to 6, and then you do it again, you get to 3 again. And if you start at 4, h of 4 is 4, so h of 4 is 4, and so on. So this is another example of an involution, and there are lots of involutions that come up a lot. One thing about involutions that we are going to care about here is what's called a fixed point, and fixed points are defined for any function, not just an involution, but a fixed point is just one of these. So one of these places where the function takes an element to itself. So it doesn't sort of do anything. It doesn't send it anywhere. It sends it to itself. So this function, this h, has 3 fixed points. So you can kind of draw what this function does. Actually, I mean, you can sort of draw what it does by just kind of making the elements and then maybe making some arrows. Let's see if I can do this. So you can sort of see that 1 is going to 2, and 2 is going back to 1. 3 is going to 6, and 6 is going back to 3. And then 4 is kind of going to itself, and 5 is going to itself, and 7 is going to itself. So this brings up kind of a fact that is basically the sort of key fact that I want to sort of wring as much use as I can out of it. But the fact itself is really it's really easy to understand if you followed along with what we've said so far. And that fact is as follows. It says that it's I mean, in sort of higher math, we call it sometimes we write this down and we give it a fancy name like a proposition. So here's the proposition. An involution let's keep it as h. So h on a set. Let's see. So if we have an involution h on a set with, let's say it has k fixed points. Must have that the number of elements of S minus K is even. And this is if S is a finite set. So what's going on here? Well, I mean, let's look at the example, right? We have 7 things in S. S has 7 things in it, and there are 3 fixed points. And what I'm saying is that 7 minus 3 is even. And what I'm saying is that's not that always happens. In other words, there's no way to make if you make an involution on, say, a 7-element set, then the number of fixed points has to be odd. And you can kind of see why that is, right? Because when I drew these arrows, right, if something wasn't a fixed point, then you had this sort of pair off. Like, you can think of an involution really as just a way to pair elements of your set off against each other. So 1 gets paired with 2, 3 gets paired with 6, but then 4 and 5 and 7 sort of, they're pairing with themselves. And so if you sort of count the elements in the set, well, all of the things that are paired off with something different, like 1, 2, 3, and 6, that's an even number of things. They're in pairs. They come in pairs. And so the leftover things are the fixed points. And so if you start with a set that has some number of elements, then the number of fixed points is the number of elements in the set minus a bunch of pairs. So if the set had an odd number of things in it, then there's an odd number of fixed points. And if the set had an even number of things in it, then there's an even number of fixed points. So that is the observation. So I'm not going to write down the proof because I just sort of said what the proof is, basically. So so that is the observation that is sort of the fundamental observation that we're making about involutions. And again, S has to be finite here. And actually you can see that if S is not finite, then you sort of don't know anything about even if there are finitely many fixed points, you don't know whether there are an odd number or an even number of fixed points. And actually 1 and 2 are an example of that. This thing here, how many fixed points does it have? Well, how many integers are there that satisfy f of x equals, that satisfy minus x equals x? Remember, a fixed point is when f of x equals x. So if x equals minus x, then the one fixed point is x equals 0, right? And everything else gets paired off. 1 gets paired off with minus, 2 gets paired off with minus 2, and so on. So this involution has 1 fixed point. But g of x equals 1 minus x, how many fixed points does that have? Well, if x equals 1 minus x, then that means x equals 1/2, but 1/2 is not an integer. So g doesn't have any fixed points. So you've got 2 involutions that are on the same set. One of them has an odd number of fixed points, one of them has an even number of fixed points. The reason that can happen is because z is because the set of integers is infinite. So, infinity is sort of both even and odd in a sense, although that's sort of not a particularly concrete way of talking about anything. So that's kind of the intuition behind it. But if the set is finite, as in this third example, then this proposition, this observation, says that the number of fixed points has to be the same parity as the size of the set. So in other words, it has to be either if the set has an odd number of elements, then there are an odd number of fixed points. If the set has an even number of elements, then there's an even number of fixed points. Now here is something that sounds even sillier, which is that in particular, if I have a set and if I have an odd number of fixed points, then there has to be at least one. In other words, if I want to show that some quantity, like that the number of fixed points is non-zero, I can actually show that it's odd, and 0 is not an odd number. So, like for instance, in this example here, it's impossible to make an involution on 1, 2, 3, 4, 5, 6, 7 that doesn't have any fixed points, because this proposition says that the number of fixed points is odd. So it has to have either 1, 3, 5, or 7 fixed points, right? And you can sort of see why that is. Again, you're pairing off things, so you can't pair off things from 1 through 7 in a way where you're sort of pairing them off with different things at every stage. There's always going to be an odd one out. at least one odd one out. So that is the key observation here. And so now we're going to use that to, first we're going to use that to go back to the brain teaser and explain the brain teaser. And then we're going to use it to prove this two squares theorem. So let's go back to the brain teaser. So I'll go to a new page here, but let's sort of summarize what we learned here. So here you can see that how many times, so the question you might ask is, let me pick a cell, and then how many times does that cell get its lock changed? Well, let's look at something like 6. When does 6 get its lock changed? Well, everything gets its lock changed at step 1, and then 6 gets its lock changed at step 2, and then it gets its lock changed again at step 3, and then it gets its lock changed again at step 6. So that's 4 times that it gets its lock changed. So how many times in general does something get its lock changed? Well, it's the number of factors that number has. 6 has 4 factors, 1, 2, 3, and 6. So prime numbers like 5 and 7, they have exactly 2 factors, 1 and themselves. So all of the prime numbers get changed exactly twice. So you can see now that if I ask you which cells end up unlocked, the answer is that the number of the cell has to have an odd number of divisors, an odd number of factors. 1 has 1 factor, 4 has 3 factors, 1, 2, and 4. 9 has 3 factors, 1, 3, and 9. Now, 1, 4, 9, you can probably sort of guess that there's another way to describe the sequence that starts 1, 4, 9, and so let's write down what we suspect. So we guess that the numbers with an odd number of factors are precisely the perfect squares. And those are the ones that get unlocked. So then, you can count how many perfect squares there are less than 1,000, starting with 1, 4, 9, and it turns out that there's 31 of them, because 31 squared is 961, and 32 squared is 1,024. So there's exactly 31 prisoners who are lucky enough to be in cell numbers with perfect squares. So why is this guess true? Well, let's sort of say that in 2 different ways. So one way to say it is, let's count factors. So let's pick a number, let's pick a cell number and count factors, so that we can go back to 6 if you like. So e.g. Cell 6, the factors are 1, 2, 3, and 6, and you can see that there's kind of this pair off between them. And the way that you pair off factors of 6 is that you look at, with 1, you look at what number you can multiply 1 by to get 6. So 1 times 6 equals 6, 2 times 3 equals 6. You could do cell 12 if you want, just for another example. 1, 2, 3, 4, 6, and 1, 2, 3, 4, 6, and 12 are the factors. And again, there's this sort of pair off where 3 times 4 is 12, 2 times 6 is 12, and 1 times 12 is 12. Now this looks like the diagram. And so again, both of these are examples of integers that have an even number of factors. They're not perfect squares. And you can kind of see that when you have a perfect square, let's do cell 16, which is a perfect square, 1, 2, 4, 8, and 16, you can see that when you do this pair off, the 1 goes with a 16 and the 2 goes with the 8, but the 4 gets paired off with itself. And the 4 getting paired off with itself is, I mean, the thing that pairs off with itself is the square root of 16. So if you want to write this more formally, you can say let d sub n be the set of factors. I've been saying factors and I'm really thinking divisors, so that's why I said d. Factors or divisors of n. Then there is an involution let's say f from dn to itself. And how is f defined? Well, f of d, well, I mean, what's happening here? 1 goes to 12, 2 goes to 6, 3 goes to 4, so, and 4 goes to 3, 6 goes to 2, 12 goes to 1. So what is the formula? Well, you know, 2 times 6 equals 12. So 2 goes to the thing that you need to multiply it by to get 12. So this involution here is f of d equals 12 over d, right? 12 over 1 is 12, 12 over 2 is 6, 12 over 3 is 4, 12 over 4 is 3, 12 over 6 is 2, and so on. 12 over 12 is 1. So in general, you get f of d equals n over d. So how many fixed points does this thing have? Well, a fixed point would be d equals n over d, or d squared equals n. So this involution has either 0 fixed points or 1 fixed point. And it has 0 fixed points when n is not a perfect square, when you can't find a d like this. And I should say, this dn, I mean positive factors. Okay, I only care about the positive ones. We don't have any step negative ones here, or step negative 2s in the prism, in the brainteaser. So it has 0 fixed points when n is not a perfect square, and it has 1 fixed point when n is a perfect square. And that means, by our proposition, by our observation, that if you want to count fixed points, or sorry, if you want to count, now you can use, so this is kind of backwards, right? The proposition said, if I know whether my set has an even or odd number of things in it, then I know that my number of fixed points is even or odd. But it works the other way, right? If the number of fixed points is even, then the set has to have an even number of things in it. If the number of fixed points is odd, then the set has to have an odd number of things in it. And that's what's going on here. When it has 0 fixed points, that means that dn has an even number of things in it. And when it has 1 fixed point, that means that dn has an odd number of divisors in it, of factors in it. And so the set of the cell numbers that have an odd number of factors are precisely the cell numbers where this involution has 1 fixed point instead of 0, because then the dn will be odd, have an odd number of elements in it. Like d sub 16 has 5 factors in it, and there's 1 fixed point. So that's kind of a nice way to use this thing to go backwards, right? You have, instead of going from the size of the set to the size of the set of fixed points, you go backwards. You know how many fixed points there are, and you deduce that that you know the parity of the set, of the size of the set. So that is the brainteaser. And so now we're going to use the same idea to go through this 2 squares theorem. So let me get to that now. So here's the theorem, and theorem is just a fancy word for fact that I can prove. So, and it's interesting and hard, I guess. I don't know. There's theorems and there's propositions, lemmas, and so on. But anyway, here's the theorem, and this I'm going to say that it's Fermat from 1640, but I will make some remarks about this. So here's the theorem. Let P be a prime number of the form P equals 4k plus 1, where k is an integer. So it's a multiple of 4 plus 1. Then the equation x squared plus y squared equals p has an integer solution. So for example, if p equals 13, say, 13 equals 2 squared plus 3 squared. P equals, I don't know, let's do 29. 29, which is, again, 4 times 7 plus 1. 29 is 2 squared plus 5 squared. By the way, it's important that P be prime. 21 is 4 times 5 plus 1, but it's not prime. And in fact, there is no solution. Has no solution. So you can check that because there's only so many squares between 0 and 21. So that doesn't work. So it's important that it has to be prime. And also it's important that it's 4k plus 1. If it's 4k plus 3, for instance, p equals 11. 11 equals x squared plus y squared. That also has no solutions. And that is easier to explain, actually. If p is 4k plus 3, and again, primes are odd except for 2. So saying that p equals 4k plus 1, it's either going to be 4k plus 1 or 4k plus 3 because everything else will be even. So this restriction to 4k plus 1 is kind of cutting out half of the primes, roughly. If you, well, roughly speaking. And it turns out that x squared and y squared are always either multiples of 4, if x and y are even, or they're multiples of 4 plus 1. So x squared plus y squared is either a multiple of 4, a multiple of 4 plus 1, or a multiple of 4 plus 2. Can't be a multiple of 4 plus 3. So it's easy to see why this is a requirement for this to have a solution, the 4k plus 1 part. The prime is not so obvious. All right, so there's a few other remarks I want to make about this restriction, or about this theorem. So the first remark is that when you say that a theorem is due to somebody, you usually mean that it's because they proved it. That's not true of Fermat. Fermat has a nice track record of being credited with theorems that he didn't prove. There's another more famous one that you may have heard of that goes the same way, that he claimed to have a proof of, but never really justified it, and wasn't actually proven until the 1990s. This one was proved about 100 years after he stated it by Euler, who is one of the sort of titans of early mathematics. I'm not going to give you his proof because it's a little bit tricky and elaborate. So the proof I'm going to give you is much more basic. The other remark I want to make before we start on the proof is that if you look at this, if you look at decompositions of P like this, you can kind of see that one of these squares has to be odd and the other one has to be even because they add up to an odd number. And so x squared plus y squared equals P. I mean, you can, if you want, you can specify that x is odd and y is even. And if y is even, then you can write y equals 2z. And so really, you're solving something like x squared plus 4z squared equals P. That's going to come up in a second. So saying that this has a solution is actually the same, and when P is odd is actually the same as saying that this has a solution, because without loss of generality, as we say, we can assume that y is even and x is odd. All right, so here's how we're going to prove this. And it's kind of clever, but the real cleverness comes at the end, as you'll see. But here's the idea, and it uses involutions. So here's what we're going to do. We're going to write down a finite set, and I'll tell you what that set is in a second. And so the proof is we're going to find a finite set S, and I'll tell you what S is in a second, and an involution with an involution F on S, such that the fixed points of f are solutions to x squared plus y squared. Well, actually, it's going to be x squared plus 4z squared equals p. And then, so that's the first sort of task, and that's not hard. I'll show you how that works. And then we're going to show that S has an odd number of elements in it. And if we can show that S has an odd number of elements in it, then the number of fixed points of that involution will have to be odd. And in particular, it will have to be not zero. And that will be the proof, right? We're trying to show that there is a solution. So in fact, what we're going to show is that in some sense, the number of solutions is odd. a lot more than we had to show. We just had to show there was at least one, and we're showing, in fact, that there are an odd number of them, which is kind of cool that, and is not the only time in math where it sort of turns out to be easier to prove something sort of bigger than you need. You just want to show that it's not zero, and what you end up doing is showing that it's odd. But how are we going to show that S has an odd number of elements? Well, actually, what we're going to do is we're going to write down a different involution on S, and we're going to show that that involution has exactly one fixed point. So then it's sort of a two-step process. We start with this, so we're going to have then find another involution, G on S, with exactly one fixed point. And then it's kind of a sort of a two-step argument. G has one fixed point, so then S has to be odd. S has to have an odd number of elements because of the parity argument, because of the parity observation. And then since S has an odd number of elements, this other involution also has an odd number of fixed points. But the fixed points of that involution are exactly the things we want. All right, so let's write down what this actually is. So first of all, S is going to be the set of triples of integers, of positive integers. So this is like an ordered pair, except it's an ordered triple. So let's see, I want x, y, and z to be positive integers. And I want x squared plus 4yz to equal p. Now, this is some set, and it's finite, right? Because if x and y and z are all too big, then x squared plus 4yz is going to be bigger than p. So depending on p, there's, like x, you can sort of see already that like x, y, and z all have to be smaller than p, because if they're at least p, then the left side of this equation is way too big. So, okay, so that's the first. So that's the first thing, is that S is finite. Now, one thing you want to notice is that S, you want to know that S actually has something in it. I mean, I wrote down, why does this equation have solutions? Well, it turns out there's one solution that you can write down immediately, because you know that P is 4K plus 1. So since P equals 4K plus 1, it turns out that 1K is in S, right? Because 1 squared plus 4 plus 1 times K is 4K plus 1, and that equals P. So this equation, we don't know yet that this equation has solutions, but we do know that this one has solutions, 1K. Now, what is F going to be? Well, F is going to be kind of the, some mathematicians sometimes say the obvious this or the obvious that, and it's a sort of a loaded word, because you don't want to make somebody feel bad if they don't think it's as obvious as you think it is. But let's just say it's a natural involution. And the natural involution is, well, if you look at this equation, y and z are kind of interchangeable. So let's let f be the involution that interchanges them. So f of x, y, z equals x, z, y. The point is that if x, y, z solves this equation, then so does x, z, y, because if x squared plus 4yz equals p, then x squared plus 4zy equals p, because multiplication is commutative. So for instance, what does the involution do to 1, 1k? It takes it to 1k1. So that's another element in S, 1k1. Okay, so that's, we're almost done, except for the hard part, which is we have to write down what G is. So hopefully you agree by now that if I could write down G, if I could write down an involution G from S to S with exactly one fixed point, then I would be done. So let me do that. This is the part where maybe you you feel a little bit of a bait and switch because you're sort of following along with everything, and then I'm going to produce this G, and you're not gonna. It's going to come from out of nowhere. Whereas, like, you know, the definition of S, which I will just remind you, is just at the top of this paper is X is ordered triples, and X, Y, Z are positive integers. And X squared plus 4YZ equals P. And so all we need to do to finish the proof is to show that there's some involution G on S that has exactly one fixed point. All right, here we go. Here is the involution. You're not going to like it. Or maybe you will. So here's my involution. I need to tell you what happens to X, Y, Z. All right, it's three cases. Here's one case. X plus 2Z, Z, Y minus X minus Z, if X is less than Y minus Z. Or it could go to this, X minus Y plus Z, if Y minus Z is less than X is less than 2Y. And finally, if X is bigger than 2Y, X minus Y plus Z, Y, if 2Y, if X is really big. There you go, that's it. So there's a lot of things that you have to check. For instance, okay, this is a rule that takes things in S and takes them to some other ordered triple. But why is this ordered triple in S? Well, you got to do some algebra, right? So for instance, what you have to check is that if you take this squared plus 4 times this, you get X squared plus 4YZ. I could probably do that real quick, right? X plus 2Z squared plus 4 times Z times Y minus X minus Z. Well, let's expand that out. That's X squared plus 4XZ plus 4Z squared plus 4ZY minus 4ZX minus 4Z squared. Okay, well that and that go away, and that go away. And look at that, I get X squared plus 4YZ, which is P. Okay, well, that's something, all right. And then, you know, you can check that the other ones are like that. There's also, the other ones also sort of give you this sort of semi-miraculous looking cancellation if you do the algebra. Another thing to check is that, is that all of these things are positive. So you can sort of see X less than Y minus Z means that this thing is positive. And same thing with these, you can kind of see that they're all positive. One thing I'll say is that if this thing holds, then this thing turns out to be in so this is like sort of three regions, three kind of possibilities, and the first one goes to the third one, and the middle one kind of goes to itself. if that makes sense. So an ordered pair that satisfies x is less than y minus z, g, or ordered triple, g of that ordered triple will satisfy this. Well, the second coordinate, 2 times the second coordinate will be less than. You can actually see that 2 times z is less than x plus 2z. Anyway, that's another thing to check. Another thing to check is that x can't equal y minus z, and x can't equal 2y. And it turns out that the reason that that's the case is because p is prime. For instance, if x is 2y, then you get 4y squared plus 4yz equals p, and you can factor out a 4. Then p is divisible by 4, which is impossible. And you can check the same thing for y minus z. You would get that if x equals y minus z, you end up getting p equals y plus z squared, which primes can't be squares of y plus z, which remember y and z are both positive, so y plus z is at least 2. Anyway, I'm glossing over a lot of details that you need to check here. One thing that we do have to check is what the fixed points are, and it turns out that the only fixed points are here, and those fixed. It turns out that the one fixed point of this thing is our old friend. So the only fixed point, and this is again another detail that I will leave to you, of G is our old friend 1, 1, K. And you can see, right, that for 1, 1, K, let's see, y minus z is 1 minus K, x is 1, and 2 times y is 2, so this inequality holds, so we're in this area. And then 2y minus x is 1, y is 1, and x minus y plus z is 1 minus 1 plus k, which is k. So you can see that g of 1, 1k is 1, 1k. So you can see that it's a fixed point without much trouble. Checking that it's the only one is a little bit more work. So again, I'll leave that to you. All right. That is the end of the proof. And that is kind of, you can see that, again, let me summarize what we did. We had this basic idea about involutions where the parity, the oddness or evenness of the big set was the same as the parity of the set of fixed points. And that's a really, really sort of basic thing. At least it was when we first introduced it. And then we souped it up and jazzed it up and wrote down this really kind of, again, completely out of nowhere involution that had exactly the properties we want to show that there was a solution. So, yeah. So I would not expect anyone to sort of understand like where this came from, and there are actually there's some papers online that I can refer you to. There's some explanations of like, well, how did they come up with this? Where did this come from? You know, that they didn't just kind of like sit around thinking, oh, what kind of random thing can I write down? I mean, this actually came from something that was a little bit more natural. That was sort of, there was some motivation for it. But you know, that's a long story. So, all right. Let me finish the video here by just talking a little bit about this theorem. And talking about some generalizations. So again, this is going to not have anything to do with involutions or this proof, but it's such a beautiful and an important theorem that I want to sort of go into some more detail about it once we have proved it. So the first remark is that most mathematicians wouldn't, if you ask them to explain why Fermat's two squares theorem were true, they would not give you this explanation. They would give you a different explanation, and many of them, I suspect, myself included, would say, "Why is this true?" Well, really, the right way to prove this theorem, quote unquote, the right way, is to say, here is my expression. What I really should do is like, this P is like a prime. What I really should do is like factor this and then see what I can deduce from that. To factor this, I need to use complex numbers, right? Where I is the square root of -1. This is sort of a difference of squares. And then I need to think about like properties of things that look like x plus yi, where x and y are integers. This is a set called the set of Gaussian integers, named after Gauss, another titan of early mathematics. Um, and uh, and there's a proof that sort of, if you know enough about the properties of the set of things like this, you can kind of you can kind of prove that this has a solution without a ton of trouble. I'm not going to go into that proof, but it really is kind of the most natural way to consider this. Um, it's not the only way that it's not the only way. Obviously, and this is not. These are not the only two ways. There's many other proofs. Euler's proof is sort of different from both of these. And then there's a beautiful proof involving what's called the geometry of numbers that I am not going to get into either. But one thing I will remark, though, is that many of the proofs of the theorem that you'll see that aren't this one involve the following fact. There's a fact that that if P is a prime, then I can find an A. There is an integer A such that A squared plus 1 is a multiple of P. And in fact, I believe that you can take A equals P minus 1 over 2 factorial. You can show that that P minus 1 over 2 factorial is always a multiple of P. Sorry, P minus 1 over 2 factorial squared plus 1 is always a multiple of P. We didn't need that fact, actually. In fact, sort of the proofs of the theorem that aren't this proof, they don't use that P equals 4K plus 1. What they use is this fact. That's kind of what they use. Whereas our proof really used this 4K plus 1. There's this 1K that was in S. So I think it's kind of interesting. Okay, two more remarks, and then we'll kind of we'll finish. Another remark is you might say, well, okay, maybe three more remarks. I'm cheating. I want to say three more things. So one thing you can ask is, well, okay, I know that which primes can be represented as sums of two squares. And the question is like, well, which integers can be written as the sum of two squares if I don't restrict to primes? It turns out that basically the hard work in answering that question is done by Fermat's theorem. And a characterization of the integers that can be written as a sum of two squares is basically that if you factor it into primes as a product of primes, then if there are primes that are 4K plus 3 that appear in the factorization, then they all appear with even exponent. Another thing that you might ask that's pretty natural is how many solutions are there to this equation? And it turns out that for P prime, that there's basically only one. And when I say basically only one, I mean like 29 is 2 squared plus 5 squared. It's also 5 squared plus 2 squared, but that's like kind of a trivial rearrangement. It's also like minus 2 quantity squared plus minus 5 quantity squared. Again, a trivial kind of like put a negative sign on one or both of the x or y. But aside from that, that's the only, the 2 squared plus 5 squared is the only way to get 29. Aside from rearranging and putting negative signs on things. And that's true even for very large primes. Even very large primes, there's only one way to write them as a sum of squares, sum of two squares. You might ask, so a couple of more things that you might ask. One thing you might ask is how many, so not everything can be written as a sum of two squares. Can everything be written as a sum of three squares? Which integers can be written as a sum of three squares, as a sum of four squares, as a sum of five squares? And it turns out that there are theorems that tell you which integers can be written as a sum of not just two squares, but of three squares and four squares and five squares. And it turns out actually that four squares gives you everything. There is a theorem of Lagrange that says that every integer, every positive integer, is a sum of four squares. And in fact, there's a generalization of that called Waring's problem that asks, um, is every integer the sum of a fixed finite number of cubes of fourth powers? And more or less the answer is yes. Every integer is the sum of at most 9 cubes, positive integer. Every positive cubes, I should say. And there are, you can replace the 9 by larger and larger numbers if you make it fourth powers, fifth powers, and so on. So this sort of humble theorem from 1640 is kind of a nice introduction to vast generalizations, vastly more powerful questions that you can ask and that have been answered. But the answers to those questions are by no means easy or obvious, but they're kind of natural. I mean, and again, the other lesson I want to take away from this is that none of what I have said here required you to know any real sort of what some mathematicians sometimes call heavy machinery. You don't need to know any theory. You don't really need to know. All you need to know is really sort of what a function is and what a prime number is. And you can theoretically understand everything that we did in this talk. That's what mathematicians mean by elementary. Elementary doesn't mean easy. It means requiring no fancy theory. So yeah, that's the summary of the talk. If you have questions, feel free to ask me. Let me know, and you can look up this paper of Zagier, and I believe that his proof was a generalization of a mathematician named Roger Heath Brown, and this was from the 1980s. But the paper is called something like a one-sentence proof of Fermat's two-square theorem, and it's a very long sentence, but but it is in fact one sentence. The paper itself is a little bit less than a page long because he has a few remarks about what's going on. But yeah, you can find that online. I just found that online before I gave this talk. I think that's everything. Yeah, if I don't see you, have a good summer, and yeah, see you next year.